Hello, in this video we're going to talk about oxidation reduction reactions now that we know oxidation states, and then we'll go beyond that to talk about half reactions, which is a useful method for figuring out what's going on in a redox reaction. Okay, so we want to think about the reaction as a whole now that we know oxidation states, and the first thing to do is find the oxidation state for everything. All right, magnesium 0, we know that the chloride's -1, it wants to be -1 at least. We don't really know about the cobalt, but if you look it up, the oxidation state for cobalt is happy to be +2, so that's a good guess. And the same thing's true with magnesium chloride, right? All right, magnesium can be +2. That's on the priority list, right? That in a compound it wants to be +2. And then the chlorine, all right, -1, that makes sense. This is pretty straightforward. It works out easily. The cobalt's 0. Okay, so what's doing what here? So if you look at it, I always start with the one that's reduced because that works better in my brain. And if you look at the cobalt, it goes from +2 to 0. That number goes down, so the cobalt's reduced. Now we need to find out what's oxidized. If it's oxidized, it loses electrons. Oxidation is loss. And that means the charge goes up. So let's see here. The magnesium goes from 0 to +2. That charge goes up. So that means the magnesium's oxidized. All right, then we can flip this around and think about the oxidizing agent. Since cobalt's reduced, that means it's the oxidizing agent. And we usually just list the whole compound here, because this whole compound brings the oxidation to the party. The chlorine just kind of watches, the cobalt does the work, but overall this whole compound does the oxidation. So we usually list it like the whole compound. And the reducing agent here is just magnesium. It starts out as an element, so that's fine. So this is easy if you have an ionic compound, right? Now, the next step here is we can talk about molecular compounds, and this gets potentially more difficult. You do the same kind of idea, it can just get messy. So first we have to assign oxidation states. And so in the octane over here, I'm going to start with the hydrogen because that's on the priority list. I know that hydrogen is going to be +1, and there's nothing else in that compound that's higher on the priority list. So hydrogen's +1, great. Now to find the carbon, we have to use the hydrogen and use the fact that when you add these together, it's equal to 0, because the molecule has no charge, so the sum of the oxidation states is 0. So 18 times +1 goes right here, and 8 times whatever the carbon is equals 0. And so if you can solve for whatever this carbon is, then it turns out that carbon is -9/4. That's a weird number. But it works because, again, these oxidation states for a molecular compound are very arbitrary, and they're just kind of a bookkeeping tool, and so sometimes you get weird numbers out of it. Then the oxidation state of molecular oxygen is 0 because it's an element. In this carbon dioxide compound, we know that oxygen is -2. Carbon is not on our priority list, so then we can use the overall sum of these oxidation states being equal to 0 to find that carbon's +4 in this compound. And then for water, well, hydrogen's +1, oxygen's -2, that works out pretty well. So now we can look at this, and I always start with the one that's reduced. Let's see here, the oxygen starts at 0, and then it goes to -2 in both compounds. So we can say that the oxygen's reduced. Then we look and say, all right, we have carbon and hydrogen left. It looks like the hydrogen is staying the same charge in both compounds, or the same oxidation state, I should say. So then carbon's the one that's changing. It goes from -9/4 to +4. And so since that number went up, it means it shed electrons, so that's oxidized. And then we can switch this around. The oxidizing agent is O2. It makes more bonds to oxygen when it reacts. That makes sense. And then the reducing agent is, in this case, the whole octane molecule. We like to call the agent to be the whole molecule, even though the carbon's the one that's actually making the reduction happen. It's making oxygen get reduced. Okay, so now let's think about this a little more. There's 50 oxygen atoms in this reaction, 25 O2, so that makes 50. And each one of these oxygens goes from 0 to -2, so it means each oxygen atom gains 2 electrons. And since there's 50 of them, that means there's 100 electrons total that are moving in this reaction. And where do they come from? Well, they come from the carbons. So that's the one that's being oxidized. And so each carbon goes from -9/4 to +4. So 4 minus -9/4 tells you what that change is. And so each one of these carbon atoms loses approximately 6.25 electrons. And again, this is kind of a weird number, but it's an arbitrary system, so you can sometimes get weird things out of it. And so since there's 16 of these, if you take 6.25 multiplied by 16, hey, your carbon atoms are losing 100 electrons total that are going to the oxygen. So these numbers here, the number of electrons must match. You are sending electrons from the carbon to something else, and so you can't like magically gain or lose electrons along the way. So this is an important feature of redox reactions that we'll get to here in this video and the next video. So now that we can think about how to make sense of redox reactions by looking at oxidation states, we can take this to the next step, which is to define a half reaction, or actually two half reactions, because two halves make a whole. And so the example here is you have magnesium solid plus oxygen to make magnesium oxide. The oxygen is reduced, it goes from 0 to -2. So this is the reduction half reaction. The magnesium is oxidized, 0 to +2, so that's oxidized. And what we do is we just kind of take these ideas from each of the oxidation piece and the reduction piece, and then we put them into separate reactions that we call half reactions. And so in this half reaction for the oxidation, magnesium, there's two of them in the reaction, it goes to 2 magnesium 2+ ions, and then in order to do that, it releases 4 electrons. So oxidation is loss of electrons. That puts electrons as a product. Now the oxygen over here, it goes from 0 to -2. So in order to do that, it has to gain 4 electrons because there's 2 oxygen atoms here and each one gains 2 electrons. And so this is the reduction half reaction. Now we split these into half reactions because it's a useful tool to understand what's going on in the reaction. Sometimes this is physically reasonable. Especially if you have an electrochemical reaction, say in a battery, where you physically separate the two half reactions and link them together with wires for the electrons to travel through. Other times, this doesn't make any sense to talk about it in terms of half reactions. Well, I shouldn't say it doesn't make sense. It's not physical, like it doesn't match the reality of how the reaction works to talk about half reactions, but it does make sense and it allows us to think about the oxidation and the reduction parts. So let me scoot this up. So in the half reactions, you have two things that have to happen. One, the number of electrons have to be the same in each half reaction, because ultimately the electrons here are going to the oxygen atoms, so you need to have the same number. Also, your half reactions have to add to the overall reaction. So let's add this together, and now you can cancel out things that are present on both sides. So the electrons, which this number should be the same for both the half reactions, those will cancel out. This leaves us with this reaction. And then since this is an ionic compound, well, we can take the magnesium 2+ and the oxide anion and throw them together to make magnesium oxide. And this gets us back to our original reaction that we started with. Okay, our half reactions add to the overall. So starting from this example and going a little farther, how do you identify half reactions? Well, first is find the oxidation states for everything, and then use that to figure out what's oxidized or reduced. Then you take any compounds containing the oxidized element and throw them into the oxidation half reaction. Then you take compounds containing the reduced element and throw those into the reduction half reaction. And if possible, avoid splitting up compounds. We had to do this in the previous example because in the product, the magnesium oxide, one part of it was oxidized, one part was reduced, and so we need to throw those into separate half reactions. But if you can, leave the compounds together within one half reaction. Then, so you have the elements thrown down, then now you need to put electrons in so that the overall charge on both sides is the same for your half reaction. And if you have an oxidation half reaction, that means you're losing electrons, they're products. And if you have a reduction half reaction, it means you're gaining electron as reactants. And then in the next video, sometimes you're asked to balance the half reactions, and so you could do that. So here's an example. Before balancing, let's write the half reactions for hydrogen peroxide and iron. So first, oxidation state time. This is a pretty straightforward application. Second, we take the components that are oxidized and the components that are reduced and throw them into two reactions. So the charge on the iron went up. That means it's oxidized. And so it goes from iron 2+ to iron 3+. So whatever's on the left side of the half reaction needs to be on the left side of your overall reaction as well. So keep that in mind. Then this goes to iron 3+. The product needs to be from the product side. Then the reduction half reaction, well, we have hydrogen peroxide. and then we have water, because the hydrogen's just coming along for the ride, the oxygen's going from -1 to -2. Now we can add electrons. In order for the charge to be the same on both sides of this reaction, you have to make an electron go here so that -1 plus 3 makes +2. And also, it's the oxidation half reaction, so it's going to lose an electron as a product. From the reduction side, well, each oxygen goes from -1 to -2, so you're adding 1 electron per oxygen. So you take hydrogen peroxide plus 2 electrons, it makes H2O. And this is all we know at the moment, is how to split these into the 2 half reactions and identify that. Looking at these, we see that the iron only loses 1 electron, whereas the hydrogen peroxide gains 2 electrons, so that's sketchy. So we're probably going to have to multiply this half reaction, and thus the irons, by 2. We also have balancing problems. If you look at this, there's 2 hydrogens on the left, 2 hydrogens on the right, 2 oxygens on the left, only 1 oxygen on the right. And there's not anywhere else for us to get more oxygens from. So this is, at the moment, inherently unbalanced, and we'll have to balance it later. So that's often the next step, is you have to balance these half reactions using various methods. The method that your book uses is the method of half reactions, which I try to keep this stuff similar with the book, so I'm just going to use that here. And we talk about that in the next video. But for the moment, you know reactions, how to identify what's oxidized and what's reduced, and how to pull those into half reactions. Then from there, we'll work on balancing, and then we'll figure out what we do with these next. All right, thanks for watching.